Okay, so we were working on this question here about Felix Baumgartner, the jumper who skydives from really, really far distances above Earth. And you should read through this whole problem from beginning to end as you go. And so here is the first equation. I'm going to assume you've already done that. And so we want to show when s is 0, the displacement, that the velocity is 10. And we want to, first we have to show the chain rule that this is indeed true. So I'm going to actually jump to where I have here. So what I do know is that v of t is equal to the derivative of ds dt, derivative of displacement with respect to time. That's the definition of velocity. So then if I say dv dt has to be ds, I want dv ds times ds dt, because those cancel to get dv dt. What this here is velocity. So dv dt is equal to the velocity times dv ds. So we can see that is there. So now assuming that g is constant, we want to solve this differential equation. So in order to do that, I'm going to start with my equation, and I know that this is g is like a number like 2. It's actually 9.8. But if I have v dv ds equal to my constant, well, if I'm going to solve this differential equation, I'm going to multiply both sides by the ds. And so when I do that, I get v dv is equal to g ds. And I want to take the integral of both sides. This is separating separable variables differential equations. And so v's and dv are together. They're the only variable on this side. This is a number, so like 5 or 9.8 ds. So I can integrate each side independently. So when I do the left side, I add 1 for exponent, and I divide by the value is equal to gs. And then somewhere along the line, I have to add c. And so now if I use my initial condition, which if I recall back from the question is v is 10 when s is 0. So when v equals 10, s is equal to 0. And so 1/2 times 10 squared plus g times 0 plus c. So this is 50 is equal to c. And so what I can say overall is I can say that 1/2 v squared is equal to gs plus 50, which in turn says v squared is equal to gs 2gs plus 100. If I square root it, I end up with 2gs plus 100 using separable differential equations. So using g to be gravity 9.8, determine whether the model predicts that Felix will succeed in traveling at the speed of sound at some point before s is 40,000. And if you recall, we are told the speed of sound is 330. So the speed of sound is 330. So if I could do this a couple ways. I could substitute in 330 equals, this is v equals 2gs plus 100. And when I solve, s is equal to 5551. Well, since this is less than 4,000, I can say he will reach the speed of sound. The other way I could do it is I could also, or if I change my colors, I could also do it where I say v is equal to 2 times 9.8 times 40,000 plus 100. And that gives me a value of 885, which is bigger than 330, so he passes the speed of sound. Either way is sufficient. Okay, so now it says testing this model of dv dt equals g. We want to talk about, if the model is correct, describe the shape of the graph of v against t. So if I consider what v of g from here, if I take that, what I can say is that the derivative of v, sorry, let me try that again. So if I do it down here, dv dt is equal to g. Well, if I just integrate that, v is equal to gt. Remember, similarly, if this is y dx was equal to 2, y would be 2x. It's the same kind of scenario, plus c. I know g is constant. So what I know here is that this is a y equals mx plus b. And so g is the slope. It is constant. And so the graph should be a straight line. When I look at the graph here, this does not look like a straight line. So not valid, as not a straight line. So it does not appear to be valid. All right, so then in C part, they give us a brand new model to consider. And it says we have this scenario now, this big thing here. K is a positive constant, G is still gravity, S and V are still 0 and 10. By using the chain rule idea here, solve the differential equation for V in terms of S, G, and Q. You may assume that this scenario here is bigger than 0. So what I want to do is I'm going to rearrange this equation and do the separation of variables again. Okay, so we're going to improve this scenario by using this scenario here, where I know that dv dt is equal to g minus kv squared. And I want to solve the differential equation by using this scenario to solve this differential equation. Well, I know dv dt is equal to dv ds equal to g kv squared. I'm separating and so now I'm going to multiply both sides by ds. So v dv is equal to g minus kv squared times ds. Now, if I consider this right-hand side here, there's only v's here, and I need the v's on the left-hand side. And so I'm going to divide by this whole variable scenario. So I can say that v over g minus kv squared dv is equal to ds. And then I'm going to integrate both sides. When I look at the left-hand side here, when I'm going to integrate it, what I notice is that I have to do a u substitution, because here is my u, and there's part of my derivative from v squared. So if I, over the side here, and if I'll do it in purple, if I say u is equal to g minus kv squared, so du dv is equal to minus 2kv, and if I multiply both sides by dv, that goes away. When I compare it over here, I want v, so I'm going to divide by the negative 2k du is equal to v dv, and that's what I can substitute this into here. And so when I do that, I end up with negative 1/2 2k 1 du, and this is just u, equals, on the right hand side is going to be just s plus c. When I integrate this right hand side, my constant stays out here, and I get ln u. My u, though, is g minus kv squared, equal to s plus c. And so now if I continue to go rearranging to get V all by itself, I can multiply through by negative 2k. So I say ln g minus kv squared is equal to minus 2k s plus another constant c. They're not the same c, but it's still a constant of some sort. And then I can just do raise this to the power of e. I get g minus kv squared is equal to e to the minus 2ks times a, because this is like e to the power c. Solving for v, I'm going to subtract. I get v squared is equal to e to the minus 2ks. We'll put the a here. Subtract g divided by negative k. And so v, if I rearrange it, keep rearranging, is the square root of, do this, I could say, well, this becomes positive g minus a e to the minus 2ks over k. I can say that. So this is v. Now, I am going to put in the initial condition of s equals 0, v equals 10, and g is 9.8. And if I do that, then I can say v is equal to 10 square root 9.8 minus a e to the minus 2k times 0 over k. And this says that 100 is equal to 9.8 minus a over k. And so a is equal to 100k minus 9.8, that's negative a, and so a is equal to 9.8 minus 100k. And so my function overall is v is equal to 9.8 is gravity minus 9.8 minus 100k times e to the minus 2ks over k. So there is my final v. When I go to the next part, I know from the beginning of this question that dv dt, which is the definition, that's the gradient, is going to be 9.672 is equal to 9.8 as gravity minus k times 40 squared. When I then go and solve for k, algebraically, we get 8 times 10 to the minus 5. Hence, find the value of v predicted by this model as f tends to infinity. So if we go take a look at this now, hence, find the value of v predicted by this model as s tends to infinity. So if we look at this is my equation for v. As s goes to infinity, if I analyze this scenario here, if I take this function here, right, if I take that, and if I look as s goes to infinity, this whole thing gets to be a giant negative number. In e to a giant negative number, as s goes to infinity, e to the negative 2ks goes to 0. So that means these two values, 0 times this, means this is 0. And so it means that v will end up being the square root of 9.8 over 8 times 10 to the minus 5, which is approximately 350 meters per second. Find the upper bound for the velocity according to this model, given that this is true. Give your answer to the 4 significant figures. Well, the upper limit occurs when s is 40,000. So if we plug if we substitute in for the S value, if we plug in S equal to 40,000, we do that, we know what K is. We put this into our calculator. V is equal to 9.8 minus 9.8 minus 100. K we know is that big ugly number. And we go e to the minus k is that big ugly number again, times 40,000 over the big ugly number of k. That should be 349.7. And it says to 4 significant figures. This is 4 significant figures. It must be 4 significant figures. Okay, so there is the first two parts. Then if we continue on, it says the assumption that the value of g is constant is not correct. It can be shown that this is true. So this is actually what gravity is not constant. It is shown by this. Hence, the new model is given by this particular scenario here. If S is 0 and V is 10, we want to use Euler's method with a step of 4,000 to estimate V, the value of V. Well, if I look here, part of this scenario here, it gets confusing as it's all V's and S's, and we're used to dealing with dy's and dx's. If this was the scenario, this is saying y dy dx equals all that minus something, and this is going to be y squared. Okay, and so if I want to use Euler's method, I need to divide by this y value, which is in this case v. So what I can say is that dv ds is equal to 3.98 times 10 to the 14th over v times 6.41 times 10 to the 6th minus s squared minus 8 times 10 to the minus 5 v, because I divide by v and that cancels out the exponent. And so that is what I'm going to do. And so when I do Euler's method though, this is kind of like, this is like dy dx. And so I'm going to let my x, which is s n plus 1, go up by 1. But our calculator, we know we have to do it the other way around. So this is s, this is n minus 1, and then it's plus 4,000 is my step. Whereas vn will be vn minus 1 plus 4,000 times this entire part, but I am going to have to put in like an n minus 1, an n minus 1, and an n minus 1. That goes in here with my initial value of s equaling 0 and v is equal to 10, because that is what we are told that this is true. And use estimate the value of v when s is 40,000. So that means each step I'm going to do s10, because I'm going to add 4,000 each time. And v, if I put that into my calculator, which I'm not going to do, you should end up with v is 361 or 360.0658. This is not easy to put into your calculator. And then finally, it says, suggest one improvement for Euler's method which you might increase the accuracy of the prediction. Well, if you make a smaller step, change this step to 1,000 or smaller, a smaller step will make it more accurate. Or you could try to solve this equation exactly. When I look at two-part conclusion, one factor not explicitly considered by the model in part D, which may lead to a difference in the model's prediction and the data collected. Well, there's a bunch of things that are occurring, right? One of the things that we could say is that if Felix is here, he could end up being like a ball, or he could try and push himself way out. His body position will definitely change the path. We also haven't considered wind. As he goes down, there's different wind currents up and on different layers of the atmosphere. We're also assuming that it's a perfect initial speed. We are assuming the path is directly downwards, which isn't true. So there's lots of different reasons we could give for here.